Welcome to Tools of Operations Research at Oklahoma Christian University. This is lecture number 3, in which we are going to talk about linear optimization. My name is Nick Grounds, the professor. So linear optimization is a special kind of problem that we solve, in which we're trying to solve for variables, we're trying to solve for an objective, which is a linear equation of some variables, some decisions we need to make. However, there are also constraints on what kinds of values those variables can take. So there's a restriction on maybe the kinds of decisions that can be made. However, those constraints are also linear equations of the decision variables themselves. So this is a somewhat specialized kind of problem in which we are going to try to solve a generic objective function, as long as it's a linear function of some number of variables, where those variable values are also constrained by linear functions. Now, the way we're going to introduce this material is we're going to solve these kinds of problems by hand. I'll be working on the whiteboard behind me. You can solve these problems using pen and paper methods that I'm going to teach. However, that sort of by hand calculation and solving is best done only for small kinds of problems. Particularly, we're going to limit ourselves to problems of 2 variables only. So where we have 2 variables or 2 things to decide, 2 decision variables to decide on the optimal values for, we can do that by hand relatively easily. For more complex problems, which we will get to in lecture 4, we'll want to solve those kinds of problems using a computer, which can automate a lot of the techniques that we're going to learn in this lecture and do so very quickly. Now, your optimal objective function, which may be to maximize or it may be to minimize some linear function, the key is the optimal value for that is always going to occur somewhere at the intersection of 2 or more of your constraints. That is, if your constraints say something like you can make, if you're trying to decide how many product to make in your factory, and you have 2 products, product A and product B, obviously you can't make a negative amount of either of those products. You have to make something 0 or more, and maybe you're limited by costs to make no more than 100 units of each product. And maybe you're further limited to say, because of time constraints or worker availability, the combination of what you can make between both A and B is limited to, say, 120 units. The optimal value of how many units to make, whether you're trying to, say, minimize the cost to do so or maximize the potential profit that can be made from selling these products, will always occur at the intersection of those constraints, of some number of those constraints. So obviously, the optimal value will either occur when you're making a combined A and B product of 120 units, or somewhere at the constraint boundaries of making 100 A units, or 100 B units, or possibly 0 of A or B, okay, if those are our constraints. So let's do a quick example showing how this would work and a little bit about why it works. So consider this problem. We have some objective function which I will call simply z, which is we want to maximize based on 2 possible decisions, 2 possible variables, x1 and x2. And the value of z takes on whatever value is 2 times x1 plus 3 times x2. Now again, this is important that it is z is a linear function of x1 and x2, because we have only constant numbers multiplied by those 2 variables, and those are being summed together. We could not have the value x1 multiplied by the value x2. We could not have squared values of x1 or squared values of x2 or any exponent. We could not have square roots or logarithms or anything like that. So this is a linear function of 2 variables, x1 and x2, and one which we want to maximize. Now obviously, just giving that information alone the larger the value of x1, the larger the value of x2, the larger z would be. So maximizing z would simply be picking the largest x1 and x2 values possible. Now, that's where our constraints will come in. So the constraints say there may be limitations on how large or small the values of x1 and x2 can be. To solve this problem, we're going to start by writing down these constraints and then using those constraints to construct a diagram or a chart of x1 and x2, how they relate to one another. That chart will look something like this, and as you'll see, we'll create one of these charts by hand. But this chart is simply trying to graph all those possible lines. So the x1 greater than or equal to 0, well, if x1 is equal to 0, that simply says that x1 has to be somewhere on this line, vertical line here, or to the right of it. That is, x1 cannot be negative. It cannot go to the left of this axis here. Similarly, x2 greater than or equal to 0 just says, well, if x2 being 0 is represented by this flat line horizontally here, then obviously we can only choose values that are above that line, not below it. Similarly, we take the equation or the constraint equation x1 minus x2 is less than or equal to 3. You could rewrite that if you needed to as x1 is less than or equal to 3 plus x2. Okay? And you would see that we can graph that with this line here. Okay? So this diagonal line going from the bottom left to the top right is the representation of that equation. And obviously, if we want those x1 and x2 values to be less than, that means we need to be to the left of that line. So we cannot go to the right of this diagonal line represented here. And similarly, you can take this equation, x1 plus 2x2 is less than or equal to 6, and see how that would be represented by this line, and values would have to be under or below that line because of the less than or equal to sign. Which means that possible values for x1 and x2 can only lie in this green shaded region. Because of the constraints, the 4 constraints we have here, they've created boundaries beyond which we cannot choose x1 and x2 values because they would be violating the constraints. So now that we know that these are the only possible values for x1 and x2 in this sort of strange, I would say, strange quadrilateral shape, right? Not symmetric, not really regular shaped, but it has 4 sides, it has 4 corners represented by the intersection of 2 of these constraints, different pairs of these constraints. The key is linear optimization. If the function we want to maximize or minimize is also linear in the x1, x2 space, then the best optimal value for it must lie on one of these corners. And the reason is, intuitively, if you think about if I picked a value out here in the middle of the chart, and I can achieve a better z, that is a more maximized z, a higher z value, by moving up, that is increasing the x2 value, okay, which obviously makes some sense here because the higher the x2 value, the higher the z value, then I would obviously want to increase x2 as far as I can. So I would move all the way up until I hit the boundary of that constraint. Now obviously once I've hit that constraint boundary, I can further move along that constraint line by either reducing x2 but increasing x1, or reducing x1 and increasing x2. One or the other of those would lead to a better z value. And once I've moved, let's just say it moves in this direction, once I move in that direction, it's always better to keep moving, because if I can increase z by, say, for example, decreasing x2 but increasing x1, then I would want to do that as much as I can until I hit this corner piece up here, which says I can neither reduce x2 or increase x1 anymore. Neither could I increase x2 without having to reduce x1, which moves me back along the line that I just came from, knowing that I was moving in an optimal direction. So as you can see, just intuitively, because z is a linear function, if moving in any direction inside this green shaded area leads to a better z, then by definition you would want to move that direction as much as possible. And once you've hit a boundary, a constraint, then it's obvious to see you would want to keep moving along that constraint boundary, whether it's this diagonal line here, or this one down here, or the straight lines at the bottom or the left. You would want to keep moving in the direction that increases z until you can move no further. And at that point, you've found an optimal value of z, by definition, which has to be at one of the corner values, or corners of this shaded area. So at that point, let's just show what this would look like on the whiteboard behind me. Okay, so I'm going to write down the constraint values a second time. So x1 must be greater than or equal to 0, x2 similarly greater than or equal to 0, x1 minus x2 must be less than or equal to 3, and then finally x1 plus 2x2 must be less than or equal to 6. And that led to something of a graph like this. Okay. So these four constraints created a restricted space in terms of x1 and x2. Okay. A restricted space which says all the valid values you can choose from must lie somewhere in here. So all we need to do is decide where these corners are located and test for those values of x1 and x2 represented by those four corners, which one has the maximum z value if we're trying to maximize z. So let's take, for example, the first easiest one, this corner here on the bottom left. We know what corner that is. Intuitively, that's the intersection of the first and second constraints, where both say that x1 and x2, respectively, must be greater than or equal to 0. So this point here simply represents 0, 0 in terms of x1 and x2 space. And we know z, okay, which was computed as 2 times x1 plus 3 times x2. Okay. So at 0, 0, z would equal 0, because 2 times 0 plus 3 times 0 is just 0. So that was a fairly easy corner to choose from or find. Let's look at this corner up here. So this corner up here represents the intersection of the constraint that says x2 must be greater than or equal to 0, okay? And whatever constraint was represented by this line, which should be this constraint here, okay? So now we're looking at the intersection of the second and fourth constraints. Well, the intersection of those two constraints, obviously you can solve these two systems of equations, okay? So you could say let x2 equal 0, let x1 plus 2x2 equal 6, okay? And solve that system of equations. Pretty simply in this case, if x2 equals 0, then x1 must be equal to 6, okay? So where x2 is 0, x1 must be 6, okay? I think I must have mislabeled these. So this point here represents x2, x2 being 0, x1 being 6, okay? So this is x2, this is x1. So with x2 of 0, x1 of 6, we can plug that into our z equation. x2 is 0, so that term doesn't matter. 2 times 6 would lead to a z of 12. So we already know that this corner, which intuitively we should suspect, this corner does not contain the maximal value of z. This corner might, definitely contains a larger value. So let's continue on and find the location of those final two corners. This one here represented by the intersection of the x1 is greater than or equal to 0, okay, and the equation x1 minus x2 is less than or equal to 3, okay. So obviously x1 would have to be 0 there, and if x1 is 0, okay, then x2 must be 3. Okay. So x2, 3, x1 is 0. Plugging that into the z equation, we would get z equals 9. And then the final corner is the intersection of the last two constraints. So there we have x1 minus x2 equals 3, x1 plus 2 x2 equals 6. Okay. You could probably solve that in your head, but if we were going to solve it systematically, we can solve the top equation, okay, for x1 and say that's x1 equals whatever 3 plus x2 is, okay, and then plug that into the second equation. Okay, so if x1 is 3 plus x2, then the second equation becomes 3 plus x2 plus 2x2 equals 6, which would lead us to conclude that 3x2 must equal 3, so x2 must be equal to 1, which then leads us from this equation up here to say if x1 is 3 plus x2 and x2 is 1, then x1 must be equal to 4. So this location here is represented by an x1 of 4 and an x2 of 1. Okay. Which in our z equation becomes 2 times 1 plus 3 times 4. So 2 plus 12, this would give us a z value of 14. So what we found is the maximal z value occurs at this sort of rightmost corner where x2 is equal to 4, x1 is equal to 1, thereby making z equal to 14, the highest z value compared to all other corners. And because of linear optimization, right, we know the best highest z value, or if we were minimizing z, the lowest z value, must occur at one of those boundary corner points. So we know that is the best z value. If we were to minimize z, okay, obviously given these equations, you could probably assume minimizing z would just be minimizing x1 and x2 to 0, which would make sense, and that's confirmed by the equations or the values we computed. The lowest z value occurs at x1 and x2 equaling 0 at this corner point here. Okay? Which means the corner point at the top and the corner point at the lower right are neither maximal or minimal, would never be an optimal solution of x1 and x2 for this particular z value. If we had a different z equation, we might have found a different corner would be optimal. That's linear optimization. Now, let's take a look at a real-world example that would involve linear optimization. So this was a contrived example of made-up variables and a made-up objective function. Let's consider a real-world example. So a calculator company produces a scientific and a graphing calculator. So two different kinds or two different products produced by this company. The long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. That is, we can produce and sell 100 scientific and 80 graphing calculators every day. Okay? That's the demand of the market for those products. Now, because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. So to satisfy, and additionally, to satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. So if we can sell a scientific calculator for a $2 loss, but a graphing calculator for a $5 profit, what is the optimal numbers of scientific and graphing calculators to make to maximize profit? Okay, so let's take our whiteboard. Okay. We'll begin by writing down the constraints interpreted from the word problem I just read. We'll then take those constraints and graph them in the two-dimensional space they create, and then solve for the optimal values of how many calculators to make to maximize profit by finding the corner points of the graphed shape, whatever shape that would take on, based on those constraints, solving for those corner points, finding the corner point that maximizes profit. So our objective, profit, okay, is made up of a linear equation of how many scientific calculators and how many graphing calculators we make. Now I'm going to use the term S for scientific calculators and the term G for graphing calculators. So profit is $5 for every G, okay, for every graphing calculator. So 5 times G minus, because we take a $2 loss, minus 2S. So that's the objective that we want to maximize. Okay, I'm just going to make a note here. We're trying to maximize that profit. Okay, so what are our constraints? Well, the long-term projections of a demand say that S, okay, should be greater than or equal to 100. Okay. G should be greater than or equal to 80. So these are the demands to be met. Okay. So we have to make at least this many calculators in order to meet the demands of our customers. That is, our customers need at least this many scientific calculators, at least this many graphing calculators delivered to them, produced by us. Okay? Now there's also a limitation that says S must be less than or equal to 200. That is, we cannot make more than 200 scientific calculators. And G must be less than or equal to 170. We can make no more than 170 graphing calculators. Okay? And then finally, the shipping constraint suggests that S plus G, the total number of calculators made, must be greater than or equal to 200. So we must make at least 200 total calculators combined from scientific and graphing calculators. Okay? So, these are the constraints. Okay, 5 constraints. Profit is the objective we're going to maximize. So now we can use these constraints, okay, to graph on this simple axis here, based on scientific S calculators, graphing G calculators, what these constraints limit this space to be. We can find the corner points of that limitation, that constrained space, and figure out which corner point represents a maximal profit. So the first 4 of these constraints are very simple. They simply say S must be greater than 100, but S must also be less than 200. Okay? So if we just arbitrarily pick here and here to be 100 and 200, all we're saying is S must fall somewhere between those 2 lines. It must be greater than 100, but less than 200. So after the first line, but before the second line. Similarly, graphing calculators must be somewhere between 80 and 200. I'm sorry, 80 and 170. Okay. So the G value must lie somewhere above this bottom line, below this top line, which means so far our constrained space looks like a square, represented in here. But there's also one final constraint. S plus G must be greater than or equal to 200. Okay. Now, there's a very simple way you can graph that. If we knew what the 200 value on the G-axis and the 200 value on the S-axis is, we can simply connect those. Okay. Because, after all, if we made 200 scientific calculators, then to make more than 200 calculators, we would just need 0 or more graphing calculators. So we just need, from this point, 200 scientific calculators to be somewhere above that. We just need a G to be positive. Okay? And similarly, if we made 200 graphing calculators, then to make 200 or more calculators total, we just need to make some positive number of scientific calculators. So we just need to be to the top right of this line here, which means the constrained space we're interested in, okay, is this sort of 5-sided shape represented here. Okay? So we need to be somewhere to the top right of this diagonal line, somewhere above this small section here of this horizontal line, but below this horizontal line, somewhere to the right of this horizontal line, but to the left of this horizontal line. So somewhere in this space here, which means we have 5 corner points. So we need to solve for how many S scientific calculators and G graphing calculators we need to make to be at those 5 corner points. Okay? Now, we'll start with the easy one. The top right just says, well, obviously we're making 200, the maximum amount, 200 scientific calculators, the maximum amount, 170 of graphing calculators. So 200, 170 is that point. Okay. If we plug that value in, those values into our profit, okay, so 5 times the number of graphing calculators, 5 times 170 would be something like 850, okay? So 850 minus 2 times 200 minus 400, so our profit, I'll just use P, would be something like 450. Okay? So that's the profit represented at that corner point. That may or may not be our maximal profit. We need to solve for the value of profit at the other 4 corners. Okay? So again, this value here, very simple. We're making the fewest scientific calculators we can, but the most graphing calculators we can. So 100 and 170, leading to a profit. Well, 5 times 170 is again 850. 100 times -2, -200. So that's a profit of 650. Okay? So already we know this corner point represents a better profit than this one here. Okay? So we know that's not our maximal profit. Okay? Do the last simple one. So if we're here, that means we're making the fewest graphing calculators, 80, but the most scientific calculators, 200. So 280, okay, would lead to, well, 80 times 5 dollars per graphing calculator would be $400. Okay. 200 times -2, also $400. So $400 profit, $400 loss, lead to a profit of $0 at that point. So again, we know that's not our maximal profit because we've already found a corner which represents a better profit than it. So now we need to solve for these 2 corner points. They're going to be a little more tricky and involve this slightly more tricky constraint. So what we do know is if we're on this bottom horizontal line, we're selling 80 or making 80 graphing calculators. Okay. What we don't know is how many scientific calculators we're making at that point. It's not the most, 200, it's not the least, 100, it's somewhere in between. And according to this equation, okay, it's somewhere at which we're making exactly 200 calculators. Okay? Well, if we're making 80 graphing, and 80 plus something is going to equal 200, obviously that something is 120. Okay? So this corner here is 120 scientific calculators, 80 graphing calculators made. The profit for that, okay, 80 times 5, $400. 120 times -2, negative $240, meaning a profit of 160. Okay. So again, we know that's not our maximal profit, because a profit of 160 is not as good as a profit of 650 that we know we can make. So finally, we're left with this corner. This corner, we're making 100 scientific calculators, the lowest amount we can. The graphing we're making graphing calculators somewhere between 80 and 170. Okay. Now already you should be able to intuitively know we're not going to get as good a profit here as we can up here, because obviously making more graphing calculators, going up this constraint line, would be better to maximize profit. But let's see what profit would be. Well, if we're making 100 scientific calculators, we're making 200 total, then we must be making 100 graphing calculators, leading to a profit of $500 minus $200, profit of $300. So systematically, we've taken the constraints of how many scientific and graphing calculators we can make, either minimums or maximums. We've graphed those constraints and represented the reduced space of how many scientific and graphing calculators we can possibly decide on making. We've solved for the corners of that restricted space, knowing that an objective which is linear in the number of graphing and scientific calculators to be made, any linear function must be optimized, whether you're maximizing or minimizing, at one of those corner points. So we solved for the location of each corner, calculated the profit associated with those corners, and decided which one obviously was maximized. So we know maximum profit occurs when we make the fewest scientific calculators we can, 100. Intuitively, obviously, we would want to do that because we take a loss, a negative profit, for each scientific calculator. But we make the most graphing calculators we possibly can. Obviously, we maximize profit by doing that because for every graphing calculator, we make $5 in profit. Now, what that does mean, obviously, is the constraint that we make less than 200 scientific calculators didn't, in fact, constrain how many we would choose to make in order to maximize profit. That is, that constraint was not, we'll use the term, binding, because it did not bind or really constrain the best value we would choose. Okay? We wouldn't have chosen 200 or anything above that to maximize profit. Similarly, okay, the constraint that we make more than 200 calculators total, okay, so this constraint here was not binding because we chose to make more than 200 calculators at all, simply because the two constraints that were binding were we could not make fewer than 100 scientific calculators and we could not make more than 170 graphing calculators. So total we made 270 calculators. So obviously the constraint that says you must make at least 200 was not binding in the sense that we didn't make 200 and we wouldn't have made fewer in order to maximize profit. We'd want to make as many as we could, at least as many graphing calculators. So we were only limited by the maximum graphing calculator amount and the minimum scientific calculator amount. That's the corner that led to our best profit. Any better of a profit would have lied somewhere to the left or above that corner. That is, more graphing calculators fewer scientific calculators. Okay. So that's a clear example of the kinds of problem that you might be asked to solve as a practitioner of operations research. So given some constraints, given some objective that you're wanting to either maximize or minimize to find an optimal value for, you need to choose or decide the best values for some variables, given the objective as a function of those variables, given some constraints on the values you can choose, also as functions of those variables. When all of those functions, constraint functions and objective function, are linear, meaning they're only constant values multiplied by the decisions and then those added up. So no decision multiplied by another decision, no decision raised to any power like squared or cubed or square root, no other functions like logarithm or anything that's not linear involved in any of the objective or constraint functions lead to a linear optimization problem. Linear optimization problems are solvable simply by finding where the constraints intersect and what value of the objective function occurs at those intersection points, and then which one is obviously optimal. So we solved this problem of 5 constraints by finding 5 intersection points. How we knew which intersection points to find was a product of the graph, the chart that we made, of the scientific and graphing calculator variables we decided on. And so we found the intersection of 5 different pairs of the constraints and then solved for the value of the objective, profit, at those constraint intersection points and chose the optimal profit, the maximum profit in that case. Let's do one more example. So, looks like something didn't render quite right. There, that looks better. Okay, let's say you need to buy some filing cabinets. So you have some filing, some paperwork you need to file. You have to buy filing cabinets to store them in. You have 2 options for filing cabinets, Cabinet X and Cabinet Y, 2 different styles. Cabinet X costs $10 per unit, requires 6 square feet of floor space, and holds 8 cubic feet of files. Okay, so it has some requirement in terms of how much floor space you need to set the cabinet on, and a capacity of how many files it can hold in terms of cubic feet, not feet, but feet. And then obviously it has a cost. Cabinet Y, on the other hand, costs more, $20, requires more floor space, 8 square feet, but holds more volume, 12 cubic feet of files. You've been given $140 to make the purchase. You don't have to spend it all, okay? And the office has room for no more than 72 square feet of cabinets. How many of each model, X and Y, of these cabinets should you buy in order to maximize storage volume? So the storage volume of the number of X cabinets and the number of Y cabinets we choose to buy is what we want to maximize. We are constrained, however, on, first, our budget, how much money we can spend, and second, on floor space, the square feet of floor space we have for the cabinets that we do buy. So we'll begin again, as before, by writing down the objective function, writing down the constraint functions. In this case, we'll use variables named X and Y for the 2 different cabinet types. So we'll write each objective function and constraint functions in terms of X and Y. And then we'll chart or graph those constraint equations to reveal or show visibly what the restriction on the selection of X and Y values are. So what kinds of values for X and Y are legal or legitimate to choose from. And then from that graphed restricted space, we'll solve for the corner points, the intersection of 2 or more of these constraint equations, and solve for the objective function value at each corner or each intersection point, and then choose the one which is optimal, in this case maximum storage volume. So we'll go again. Okay, so we'll start with our objective function. Okay. So the objective function is storage volume. So I'll just represent that as, say, volume, which is equal to, well, each X cabinet we use or buy gives us 8 cubic feet. So 8 times X is the cubic feet volume that we get from the X cabinets we choose to buy. So X being the number of cabinet X we buy, 8 times that number is how much cubic feet of volume we get from that. And then obviously 12Y is the volume of storage capacity we get from the Y number of cabinet Ys we choose to buy. So that's our objective. Constraint functions. Okay. First, we'll start with the budget constraint. So we know we can spend no more than, so we need to be less than or equal to $140. Okay. But we need to know how do we compute how much money we do spend. So if we're limited to $140, how much did we spend? Well, it's based on the number of X and Y cabinets we buy. And if X cabinets cost $10, then 10 times X is the number of dollars, the amount of money we spend buying X cabinets. And naturally, 20 times Y is the number or amount of money we spend buying Y cabinets. So 10X plus 20Y is constrained to be less than or equal to 140. Okay. The next constraint is that of floor space. So again, we're limited to, we can go no larger than 72 square feet, and each X cabinet requires 6 square feet, so 6X plus each Y cabinet requires 8 cubic feet, or 8 square feet. So 8 times Y, 6X plus 8Y must be less than or equal to 72. Now this is an interesting and representative problem. So far we have our objective function and only 2 constraints. Obviously, 2 constraints don't really make sense in terms of limiting or constraining a space that's 2-dimensional, X and Y. However, there are 2 assumed constraints that weren't spelled out in the word problem. You'll find many problems of this type that have some assumed constraints that you'll have to sort of figure out. For example, what's the minimum amount of X cabinets that can be bought? Obviously, we can buy no fewer than 0 X cabinets. That is, the X axis here, we have to be above it. We can't buy -1, -2 X cabinets or anything less than that. It's not sensible. And similarly for Y, you can buy no fewer than 0 Y units. So we're already constrained to be in this quadrant of the XY space. We cannot be here, here, or here. Now we can solve these equations and how they intersect with either a 0x or a 0y. So for example, 0x means that 8y would have to equal 72. Okay? So 8y being 72 just means we bought 9 y cabinets. Okay? So if we bought 0x cabinets and 9 y cabinets, we would hit the limit of our floor space. Similarly, if we bought 0y cabinets, we could buy up to 12 x cabinets, okay? Which means the linear equation here is that of floor space which says you must be somewhere to the left and below that diagonal line. That is, you can buy no more than 12 X cabinets, and even if you do, you can only buy 0 Y cabinets. You can buy no more than 9 Y cabinets. If you do, you have to buy 0 X. Anything in between, right, is just limited to be less than this diagonal line. Similarly, another equation, another linear equation for the budget. If we bought 0 X cabinets, then we could buy up to 7 Y cabinets before we would exhaust our budget. If we bought 0 Y cabinets, we could buy up to 14 X cabinets, which means we have a constraint like that, which is our budget constraint. Okay? So, all in all, we must lie somewhere in this space here, meaning we have 1, 2, 3, technically 4 corner space, or corners, intersections. Naturally, this one, 0, 0, constraints that say we can't buy less than 0 of any cabinet, would lead to a volume of 0, clearly not going to be our maximum. Buying the maximum amount of Y cabinets allowable in the sense of the budget, okay, 7 Y cabinets would lead to a value of, well, 0x and 7y would lead to a volume of, let's see, 12 times 7, 84. So 84 cubic feet. Clearly then, as you might expect, that point will not be our maximum volume. Similarly, the simple point out here where we have 12 X cabinets, 0 Y cabinets, would lead to a volume of 96 cubic feet. Okay, 8 cubic feet for every of our 12 X cabinets would lead to a volume of 96, meaning this up here, 84 cubic feet, cannot be our maximum. So now the question is, what is this point here where our floor space and budget constraints intersect? And what would our storage volume be at that point? So solve for these two equations intersecting. Okay, so we could say that 10x is equal to 140 minus 20y, which is just to say x equals 14 minus 2y. Okay, we can plug that into this equation. Well, first I'll say 6x plus 8y equals 72 is the same thing as saying 3x plus 4y equals 36. Okay? So now if x equals 14 minus 2y, according to this constraint, and we plug that into this constraint, okay, so 14 minus 2y plus 4y equals 36. Okay, which simply just says 2y equals 22, which means y equals 11. Okay. Make sure we did that right. So 10x and 40. Okay. 14 minus 2y, 6, 4, 7, 6. Okay. Oh, I'm sorry. This was 3 times that. Which means, well, 3 times 14 is 42 minus 6y plus 4y equals 36, which means 2y equals 6, okay, which means y equals 3. And if y equals 3, then x being 14 minus 2y is 14 minus 6, which would be 8. So this point here is represented by 8 x cabinets, 3 y cabinets, which leads to a volume of 64 plus 36. 64 plus 36 would be a volume of 100 cubic feet. Okay. Which means our maximum volume is located at the intersection of our budget and floor space constraints. Okay. A maximum volume of 100 cubic feet by buying 8 X cabinets, 3 Y cabinets. Okay. So that is our optimal answer. Now, that should be neither too surprising that this is our maximum, because obviously we wouldn't get a maximum volume by minimizing either x's or y's, certainly not by minimizing both. We'd want something here that bends above the line between these 2 points and gets us a better, higher value of x and y than we could find by either of these two. Okay. That's our final example for linear optimization. So linear optimization, again, linear objective function in terms of our decision variables, the things we can decide or choose values for, constraints on those variables, which are also linear functions. And the entire approach revolves around first writing everything down, understanding how to take a word problem like this on the screen, turn it into equations in terms of an objective to maximize or minimize, and in terms of constraints that limit either less than or equal to or greater than or equal to functions of the variables. Okay, we went from there to graphing. If we're doing this by hand with 2 variables, it's very simple to graph each constraint line and then represent by shading in the area, like we did here, the area that represents which values are legal or legitimate to choose, and then solving for the corner points where, by definition, our optimal objective function will always occur. Now, beyond that, next time, we will look at linear optimization of more than 2 variables, and instead of solving that by hand, we'll investigate some of the ways using the analytic solver platform you can automate that process, doing so in Excel to solve for the optimal values of your decision variables to achieve the optimal objective function value according to some objective that you can define. Thank you very much.